This video is on the quotient rule for radicals. So in our previous videos we saw how to simplify radicals. Here we're going to talk about, what if you have a quotient, meaning division, of a radical. So if I said I had the nth root of a over b, that's the same as saying take the nth root of the numerator over the nth root of the denominator. Keeping in mind that this only applies where you can take the root of each piece if you have multiplication or division inside of the radical. So we're going to use this interchangeably. We can see a radical with division inside where we might want to actually take the root of the numerator over the root of the denominator because it might be easier to work with. Or we might see this where you have the same root in the numerator and denominator. You might want to take the entire root then divide first. So we'll use this rule both ways. Let's take a look at some examples. So if I said to simplify, and the first one we'll look at is the square root of 18 over 2. Now, you could use the rule and take the square root of the 18 over the square root of 2. But if you did, you might recognize pretty quickly that you don't have any perfect squares here. So it might be easier, rather than try to take the square root of each piece first, to do the division if it divides nicely. In this case, the square root of 18 over 2 is the same as the square root of 18 divided by 2, which is 9. And the square root of 9 is 3, right? Because 3 times 3 gives you 9. So in that case, we did the division first. If I gave you this one, if I said I had the square root of 16 over 25, and it's the root of that whole fraction. Well, if I'm taking that square root, 16 over 25 doesn't reduce, doesn't divide nicely, so what you might want to try is take the square root of 16 over the square root of 25, right? That's what our rule says. We have division underneath the root. We can take the root of each of the numerator and denominator individually. Now, one of the reasons why you would want to do this, especially in this case, is you might notice, okay, the square root of 16 is a perfect square, the square root of 25 is also a perfect square. So we can simplify this pretty quickly. The square root of 16 is 4 over the square root of 25, which is 5. And so our answer here is 4/5. And notice I'm doing this without a calculator. You should be able to do this without a calculator as well. Recognizing that you have perfect squares there. What if I gave you this one? If I said we had the square root of 50 over the square root of 2. Now, 50 and 2 aren't perfect squares, but you might want to see what happens if you divide them, right? Because if I take the square root of each numerator and denominator individually, you could take it as the square root of just the entire fraction. So I could really rewrite this as the square root of 50 over 2, which then will simplify the inside of this root, so it becomes the square root of 50 over 2 is 25. And then you can ask yourself, what's the square root of 25? Well, that's 5. So here's the case where you started off with the square root of the numerator, the square root of the denominator. It was easier to simplify as division underneath the root first, and then take the square root. Some of this is recognizing what you have and knowing 50 divided by 2 will come out to a perfect square in 25. Let's say you didn't notice that, right? Or let's say you started with the square root of 50 over the square root of 2, and you said, I'm going to simplify this like I've seen in the past in previous sections. So the square root of 50, is 50 a perfect square? Well, no, it isn't. So then you want to break it down to its highest perfect square factor and the non-perfect square factor. Well, the highest perfect square is a factor of 50. And remember, when I talk about that, I'm looking at the list of perfect squares, so it's 1, 4, 9, 16, 25, 36, all of those numbers are perfect squares. So the square root of 50, the highest perfect square, it's a factor of it, it's 25 times what gives you 50? The non-perfect piece is 2. So the square root of 25 times the square root of 2. Over here, the square root of 2 isn't a perfect square. 2 doesn't have any perfect square factors other than 1, so I'll call that the square root of 2. Keep it the same. And now I'll go to simplify this. Well, you might recognize square root of 2 is the same factor in the numerator and denominator. They're going to cancel out. So you're just left with the square root of 25, which is 5. So you get the same answer. One involves just doing the division first and then simplifying. The other one, you actually simplified each root individually and then canceled and then evaluated. Both are okay. Either method you want to use there will work out. Let's just look at a few more. If I do this one here. We'll say we have the cube root of 54x squared over the cube root of 2x squared. So you might want to check to see if this divides, or I should say, you might want to check to see if these are perfect roots first. 54 isn't a perfect cube, x squared isn't a perfect cube, because remember the power would have to be divisible by 3. Same thing down here for 2, and then the x squared, again, power is not divisible by 3. So none of these are perfect cubes as they are written. But you might want to try to do the division first, because you see that you have the same root, and these have to be the same, otherwise you can't do this. So this is the cube root. Don't forget to write the 3 there to indicate the index of 3, meaning the cube root. Of 54 divided by 2, well, that's 27. X squared over x squared, those are going to cancel out. So it's really just the cube root of 27. And the cube root of 27, you know, remember, cube root of 27 is 3 to the third power, so the answer here is 3. Now, if you want to use your calculator to evaluate that, you could. Just keeping in mind that you should know your perfect cubes, right? If you're thinking of the list of perfect cubes, remember that list would start with 1, and then the next number on there would be 8 because that's 2 cubed. The next number you want to look at is 27 because that's 3 cubed. After that, 4 cubed is 64. 5 cubed is 125, and so on. So if you're looking for what could possibly be perfect cube factors, remember you're pulling from that list. Let's take a look at just a couple more. We'll call this one E. If I had the cube root of x to the 5th, y to the 8th, over the cube root of x to the 3rd, y to the negative 4. And you might want to try this on your own, so you might want to pause the video, try it out, and then come back. If I'm looking at this here, first off, I notice that these aren't perfect cubes inside of here, at least not entirely. Remember, to be a perfect cube for a variable, the power has to be divisible by 3. Neither of these are perfect cubes. This is a perfect cube. This one isn't, but you don't really want to, try to simplify as a perfect cube at this point, without at least trying a division first. So if I divide these, right, they have the same index for the root, so I can write it as one large cube root of the entire division. I would have x to the 5th, y to the 8th, divided by x to the 3rd, y to the negative 4. And what I'll do is I'll simplify the inside of this first. So it's the cube root. Make sure you keep that index of 3 out there, right? It's cube root. When you divide things with the same base, remember you subtract their exponent. So 5 minus 3 makes this x to the 2nd power. And then for y's, we've y to the 8th minus a negative 4. Remember when you say minus a negative, that you're really adding it. So 8 minus a negative 4 is 8 plus 4, so this will be y to the 12th. And now we'll go to simplify this. If I'm simplifying this here, is this a perfect cube inside of my radical? Well, x to the 2nd power is not a perfect cube. You can tell that because the power is not divisible by 3. Y to the 12th is a perfect cube. So remember how we do this. Unless this whole thing's a perfect cube, we can't just evaluate it right away. So I'm going to just organize. I'm going to put the highest perfect cube factors in the first radical and then the non-perfect cube factors in the second radical. Since y to the 12th is a perfect cube, I'm going to put it right in here. I'm not evaluating it yet. I'm just doing this to organize. X squared, right, is not a perfect cube. Does it have a highest perfect cube factor? Well, 2 is less than 3, so there are no other factors here that you can pull out as powers of 3, so this is going to stay as x to the 2nd in the non-perfect piece. And then what we'll do is we'll evaluate the perfect piece. Remember how you evaluate this. If we have the cube root of y to the 12th, remember we're just going to do 12 divided by 3, right? You take the power divided by the index. That's why we took the perfect pieces to be divisible by 3. 12 divided by 3 gives me y to the 4th. Make sure you don't put the root on it anymore. That's evaluating it. And then we're left with the cube root of x squared, and that doesn't simplify. So you would leave it like that. So we got y to the 4th cube root of x squared. And we'll take a look at just one more here. I'll call this one letter F. So if we're asked to simplify this one, the cube root of 27x to the 7th, y to the 2nd power, over 64x x y to the 17th. So if you're thinking about simplifying this, the first thing you should ask yourself is everything inside here a perfect cube, making this a perfect cube. Well, is 27 a perfect cube? The answer is yes, because 27 is, a number to the third power, 3 to the third power. Is x to the 7th a perfect cube? Well, no, it isn't, because 7 isn't divisible by 3. Y squared, again, the power is not divisible by 3. 64, yeah, that is a perfect cube, because it's a number to the third power, that'd be 4 to the third power. X isn't a perfect cube, y to the 17th isn't a perfect cube. You might be tempted to try to evaluate these perfect cubes right away. I would recommend simplifying first and then evaluating. So I'm going to simplify the inside of this, since neither of these numerators or denominators are perfect cubes completely. And I'm going to write this as the cube root of 27 and 64. Well, they don't have any common factors other than 1, so I'm going to keep 27 and 64. I'm not evaluating yet. Then I'm going to simplify the variables. X to the 7th over x. Remember, you're subtracting the exponent. 7 minus 1 gives you x to the 6th. That's really in the numerator. You could also think about it as you're canceling one of these x's with one of them here to make that x to the 6th. And then y squared over y to the 17th. Now, you could rewrite this by using the subtraction rule. 2 minus 17 would give you negative 15 for the power on y. But then the negative would tell you to move it to the denominator. If these powers are all positive, it's kind of an easier way to look at this is just saying, okay, I have 2 of them here and 17 here. I'm going to cancel 2 of these with 2 of these, and this becomes y to the 15th, and it's in the denominator. You can only cancel like I just did if all the powers are positive. If there's anything negative there, you have to actually do a division. But if I did 2 minus 15, or minus 17, you give me a negative 15, y to the negative 15 would be considered in the numerator, then be moved down here. Once you're here, you simplify the numerator and denominator completely. Let's see, are these perfect cubes now? Well, 27 and 64 we already talked about are perfect cubes. X to the 6th, yes, that's a perfect cube because it's divisible by 3. Y to the 15th, yeah, that's a perfect cube because 15 is divisible by 3. So simplifying this, the cube root of 27, remember it's 3 because 3 to the third power gives you 27. You're not dividing it by 3, right? You're saying 27 is a cube root, right? What number to the third power gives you 3? Which is 3. Or which power to the third power gives you 27, which is 3, I should say. You have x to the 6th, taking the cube root, you divide by 3. 6 divided by 3 is x squared. Over here, cube root of 64, remember what number to the third power gives you 64? Well, that's 4. And then y to the 15th. 15 divided by 3 makes us y to the 5th. Remember, you don't write the root after you've taken it. So we have 3x squared over 4y to the 5th. So hopefully these examples, help show how to simplify when you have division within the same root, or if you have divisions of 2 roots with the same index, and how you can simplify. It carries over from what we did in the previous video on simplifying radicals. It's just giving you one more step.